Here he's in the deep water, shallow, deep. So we see a semi-diurnal wave from this vantage point. Now, Newton's law tells us about this bulge underneath the moon. We have to come up with some other explanation as to why there is a bulge on the other side of the Earth. And this slide tells us that the Moon-Earth system rotates about an axis in the Earth, producing a centrifugal force and a centrifugal bulge on the other side. I don't know if you can pick up the blueness of that bulge on each side here. So that's where we get the twice-a-day tides on the Earth. So we have a mechanism now whereby we have a motion of the water on the Earth in the flood of Noah. That's not all we need, however. We need that wave to produce a motion in the sediments that are involved, because we want to lay down these layers. Now, if I go over to the next slide here, it's titled 3 Categories of Water Wave Characteristics. And I show a deep water wave situation, an intermediate, and a shallow water wave. So there's 3 different categories that are based on the depth to length ratio. Depth of the water, wavelength of the wave. Now, if we have 2 waves on the Earth in a flooded planet, then the wavelength is half the circumference at whatever latitude we're looking. And if we would have this situation with deep water waves, you would see that there's hardly any motion at the bottom. That wouldn't be very conducive to forming layers on the bottom. Well, you say, have a global ocean that is at its height, covered the highest mountains of the day. Certainly that was deep water. But compared with the length of the wavelength, it's a large D over L ratio. If we come over to the shallow water wave, the D over L ratio is about 0.05 instead of 0.5. And so we have, instead of a zero velocity at the bottom, we have a nearly uniform velocity distribution with depth. And that's just what the doctor ordered in order to move along these sediments on the bottom of the ocean.
And those sediments have been moved and have systematically been placed conformably one upon another. So we're trying to explain and run experiments to explain exactly how that could happen.
Now, I will be the first to admit that there are many local instances where you can find objections to this kind of a situation, but I'm talking about an overall situation on a very large scale in the continents.
Well said. Now that brings us to the Flume, where you and Professor Ian Juby at the museum are actually running experiments to try to replicate this.
We can't produce in a flume like this, a linear flume, or even in a circular flume like this, we can't produce tidal waves. The best we can do is to form a uniform velocity distribution along the length of the flume. We have a ramp over here, a hole in the side of the circular flume. We do our mixing of the sediments in here. There are paddles in here which we rotate and mix up the sediments, and then it comes out of the hole in the wall and down this ramp and then out the flume. This is where the experiments take place. To prepare the water and the sediments, there's a hydraulic jump at the end of that ramp, which is the excellent mixer just before we deposit the mixture onto the ramp, onto the flume.
All right, having said that, now we come to Ian Juby. Here's a photo of you in the background. Ian, would you take it from there, describe
Sure.
what you actually have been doing and what is seen in field study?
Okay. So, as Professor Clark introduced here, what we're essentially doing, we're taking mud, basically. It's sediments and water in a moving mixture coming down the flume, and we do things like vary the tilt on the linear flume itself here. Now, we brought our original small one here right up front, and it's kind of ugly and dirty, and the reason it's ugly and dirty is because we dump mud through it.
It's
That's
the
what we do.
real thing.
It's the real McCoy.
We're demonstrating actual scientific experiment taking place.
And it has been an eye-opener. Every single time we have fired these things up, we have gotten pleasant surprise after pleasant surprise
and
after
you've
pleasant
lectured
surprise.
to international audiences on the data. Tell us what you have found.
Okay, one of the things we just most recently, I guess I'll touch on this one first, from this flume here, which is the largest one we built to date, we were doing test runs. We hadn't even gotten up to speed in actually doing any experiments yet. We're just trying to get it running. And M.E and I were sitting there checking the flow, trying to see if the pumps were keeping up and everything, because we're recirculating the water. And in this case, we had not cleaned out the sediments. And when we looked up, suddenly there's all these wave ripples. Now, these are called translatant climbing beds, and I'm going to come back to these because it's very interesting how they were formed. This also ties in with the parallel layers and how they are formed in the rock record, and it all comes back to this. It's called cross-bedding.
Yes.
Now,
What an incredible phenomenon. Here you have horizontal bedding, and then you have cross bedding on these plains.
yes, and this is from Zion National Monument. You also see this in the Grand Canyon as the Coconino Sandstone. Stan Lutz and I, when I first encountered these, now Stan has had some actual professional geologic training. I have not. I'm just a passionate amateur and learned along the way. But he had never come across cross-bedding before either. We traced one layer in West Texas for probably about 150 miles, and it was only about a foot thick, but very clear layer of cross-bedded, about a foot thick. You could tell which layer it was by the layers on top and below, which were strictly horizontal layers. Now, when you take a look at these cross-bedded layers, you have your layers. There's one layer there, and there's another layer there, and then you have these angled cross-beds. Now, if you take a close look at those cross-beds, you'll notice it has three phases to it. It has the top curve, which is called the top set, curves down to the slope, which is the foreset, and then it curves off level again at the bottom set. Now, if you go to Zion National Monument, Arches National Monument, Grand Canyon, they refer to these as fossilized sand dunes. Now, immediately, that seems to pose a pretty big problem for the idea of a global flood. According to creationists, these would be flood layers.
Yes.
So how on earth are you going to explain fossil desert dunes in the middle of a flood? Well, first of all, if it's a fossilized sand dune, it takes a lot of water to fossilize a sand dune.
Yes.
It's not going to happen without water. Now, within the layers, not so much in Mount Zion, but within the Coconino, we have fossil footprints, which I'm going to show you some examples in a second. Some very unusual things about those footprints. They only ever go uphill. Sometimes they even crab track like these, where the animal was walking sideways with its toes going uphill.
Yes.
What on earth is going on here? Within the space of 3 or 4 feet, those tracks will go from very heavy impressions to lighter to claws only to completely vanishing. What is going on here? I mean, if it's a desert...
Yes, if it's a desert and...
Did the lizard evolve wings and fly away all of a sudden, or was it a very impressive weight loss program? What happened?
So the standard explanation is not sufficient.
It doesn't. And in fact, Dr. Derek Yeager that you mentioned tried to explain that away by saying only the tracks on the lee side of the sand dunes were preserved. The ones on the windward side were destroyed by the wind. That doesn't make any sense if you follow it through. That means the animals had to walk in one direction in the desert at all times. It's nonsensical when you stop and think about it logically. But let's compare it to modern day sand dunes. Now, this is a sand dune out in the middle of nowhere in New Mexico. I don't even know where this was. It was beside the highway. But somebody conveniently cut through it with a bulldozer. I got to send them a thank you card. I really appreciate that. And inside, you can see the layering is not cross-bedded. It follows the contours of the sand dune.
Yes.
So wind does not produce cross beds. This is an example of a wind-blown sand dune.
Right.
So what's going on there? We took our flume, the small one up front actually is what we took, And while we were running the experiment,